Thanks for the kind introduction. I hope that I will stay within this and talk only 12 minutes. Basically, it's a little bit weird to be in theater and to give a presentation on brushes, and I thought of making a joke. Theater, mass spec, like far field or near field, the question is now. So this is what I'm going to be talking about, basically polymer biomaterials, and the thing that we are dealing with for quite a long time, and that is to somehow emulate the function of the extracellular matrix and bring some information or artificial information to the cells which are trying to attach on the surface. What is the design of our surface? Basically, it's some carrier, which we'll always have to support the cells. Some material, which we call polymer brush, which suppresses any non-specific interaction between the cells in the human body and our material. And some bioactive ligands, mostly peptides, which are bounded on the surface. Just that I show you what I'm talking about is real and that we know what we are doing is to show you this basically woven PET material which you would normally get if you get a reconstruction of your blood vessels. So this is the PET material, the construct. This is the PET material with our brushes which completely suppress the non-specific interaction. And this is the bioactive brush which has the peptides on top of the material. And you can see how we re-establish the binding of the cells. I said that I'm going to talk about polymer brushes. What are they? They are densely packed polymer molecules. So all the results that you will see, it's a monolayer of polymer which resides on the surface, which is performed by either grafting of the polymer chains directly on the surface, or growing the polymer chains from the initiating sites which are present on the surface. This is our toolbox. Basically, you name the chemistry, we will perform it for you, we will put it on the surface, and we can perform the far field characterization, either ellipsometry, XPS, FTIR, SFG we tried, electrokinetics. But what interests me the most is basically this. Can we observe chemical signatures of the polymer chains, which are basically on the nanometer scale? Can we define the orientation of the polymer chains which reside on the surface? And can we observe and map the presence of bioactive components over the surface? Yes, there are different methods how we can achieve this. We do quite a lot of single molecule force spectroscopy, but we can say only what is going on, what is the length of our polymer chains, no chemical information. We can do some radioactive radio labeling, and we can say something about the amount of peptide that we have on the surface, but we already modify the chemistry of the surface. Or we can use gold nanospheres and again indirectly say about the spatial distribution of our peptides over the surface. Something that Fritz always likes to criticize and say like, but why spectroscopic sSNOM imaging when you have palms and storm? Yes, we have them, and they gave us the power for a super resolution, but super resolution on the side of the cell. It doesn't tell us anything about the material underneath. So let's go through the journey, observe the chemical signatures of the polymer chains. One of the most boring slides that I have, basically grafted from brush and something which thrilled Adrian quite a lot, to see basically almost one-to-one match between the far-field spectra and the near-field spectra measured at few points. As I said, normal distribution of the vibrations over the surface. And this is a slide, the next one, performed analysis, sSNOM analysis, for the grafted two brushes, PEO brush, anchored to polydopamine. We will hear a little bit more about polydopamine in the next presentation of Dr. Dendisova. But this is the slide which almost ruined my career. Adrian was coming with a broad smile and was telling me, Ognen, your brush has holes. See how it looks like. And it's consistent, you know. This is the signature of the most, the strongest vibration on the PO chain. This is a shoulder in the far field spectra, and this is just something coming from the anchoring layer. Good. Then somehow we've agreed that, that we need to perform some nano-FTIR analysis and go over this line from something which call the hill, an area which we call the valley, and additional hill. And with a strong push of Fritz, we were capable not only in saying that basically in the valley region, we really have polyethylene oxide, which would not be visible or obvious when we look only on the height image of the AFM, but we were capable of observing that the valley also has spectral signature of the PEO. We pushed even further. So we said, let's see, and to define the orientation of the polymer brushes. So please visit the poster of Dr. Jan Svoboda. We can talk more about how we did the orientation and stuff. Basically, we took into account that we are sensitive to the spectral contributions with transitional dipole moments oriented parallel to the field. We did some calculation. We optimized the most energetically favored components which we have for conformers. We calculated their infrared spectra, and voila. What we got is that in the hill region, basically most of the chains which we have are perpendicularly oriented to the surface, where in the valley we have something like 50 to 50%. And this is basically, of course, we are not probing individual chains, but we are going from something like 800 to 400 chains which we sample. Let's try to observe if we can directly see the peptide sequences over the surface. This is a peptide which is characteristic basically for targeting embryonic cells, stem cells. It was bounded to the surface by click reaction, so it was bounded to something what we call a hierarchical brush. Again, we have this monolayer of polymer, with only the second block of the polymer being capable to undergo this click reaction. And we click the peptide. This is the far field spectra of the peptide. This is the polymer brush. And these are two concentrations of the peptide over the surface, something like 450 nanograms and 10 times higher, 4,500. Let's see the sSNOM images. The pristine brush, basically no features, and different features observed over the surface, the bioactive surfaces when we have low and high concentration of the peptide. Even more and more interesting, basically this change in the contrast images at various vibrations, amide 2, amide 1, amide 2, and I don't know the hell from where comes this one. This is a thing that we are still fighting with. We did the nano-FTIR analysis, and we scanned over the features, the mechanical features which we observe. But I still, as I said, I still do not have answer of precisely from where comes this, this specific vibration at 1589. Is it some orientational effect that we observe or not? That's for now it. But what I wanted to show, it's basically not only the direct mapping, but basically the guess, the hint that we have about not only the lateral distribution of the peptides along the surface, but basically the Z height. And if we take that, the penetration depth of the different overtones, it's from 60 to 35 and 25 nanometers, basically we can, and keep in mind that we have basically no, or rather even distribution on the pristine brush, basically we see nice effects on the signals which we get on the second and the third harmonics with respect to the first one, which to me to some extent indicates that really we have the block copolymer structure, and the peptides basically are exposed on the surface of our polymer brush, indicating that we will have strong interaction between the approaching cells and our materials. Basically, by this I will finish my talk. I led you through our main results within the field of polymer brushes and bioactivity of polymer brushes. I would thank my team, and 12 minutes, Marcus, you do not need to even stand up.